Okay, activity 29, talk about counting principles. So we're going to figure out how to count up how many different things can happen uh, with different scenarios. And so I'm going to show you how to break that down and work from there. So let's just, each answer needs to be explained here. So we're going to talk it out. And a lot of what we need to use in our explanation are going to be things that I say and things that you would need to write down in that. So uh, Ashley has some matchbox cars to display in a row on a shelf. She has 2 red cars, 3 black cars, and 5 silver cars. All of the cars are different models. So even though they're the same color, they are different cars. So there's no repeated cars here. And how many different orders can she place the cars in a row? So how many cars do we have? We have 5 silver, 2 reds, and 3 blacks. So that's 10 total cars. Okay, so there are 10 total cars and 10 positions on the shelf. Okay, so one good way of doing some counting principle is to make blanks for each position that they can be in. So I'm going to write 10 blanks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 positions that could be there uh, on that shelf. Well, in the first position, we haven't put a car on the shelf yet. So there are 10 cars that we could pick from. So we're going to pick 10. We got 10 possible uh, cars that could be there. They may be a red car, maybe a black car, maybe a silver car. It doesn't matter. They're all different cars. So we got 10 cars to choose from. Once we've placed that first car on the shelf, the second position, the pile of cars is reduced to 9 cars. In the third position, the pile of cars is reduced to 8 cars, 7 cars, 6 cars, 5 cars, 4 cars, 3, 2, and 1. And we want to know how many different ways there are to place those on there. We're still going to multiply all those together to find how many ways that could be placed on there. So what this is actually a mathematical notation for that is 10 factorial. And 10 factorial is it's the n factorial is taking a number, whatever n is, start with it and reduce by 1 till you get to 1 and multiplying those together. So 10 factorial is what this is, but it means multiply 10 times 9, that times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. But with your calculator, it's much easier to hit math and then go over to probability, and there's the factorial option there. And I'm gonna type in the number I want, 10, then hit math, go over to probability, and select factorial, and 3,628,800 different ways. 3,628,800 ways to arrange those on the shelf. So your explanation would be 10 positions, 10 total cars, and then you're showing that setup there. And said, B part says, in how many different ways could she place the cars in a row if the black cars have to come first? Again, we got 10 cars that we're putting in position. 7, 8, 9, 10. And then we want to put black cars in the first position. So how many black cars do we have to choose from? So we kind of have 2 different piles that we're dealing with here. So we got the pile of black cars, and we know that there are 3 black cars. So the first position could have one of the 3 black cars. So it's 3 choices. And then the black cars all need to come first. So if we used up one of them on the first position, there are only 2 left. And then there's only 1 left for the third position. And then the next position, it could be either the silver or the red cars. There's 7 of those to choose from. And then 6, 5, 4, 3, 2, 1. And again, we're going to multiply all this together. And if you look at this, we have here, this is 3 factorial times, and then this part would be 7 factorial. So you could write it, you could type all that in to your calculator if you wanted to. 3 times 2 times 1 times 7 times 6 times 5 times 4. A lot of button pushing for that. Or you can use the factorial button. So 3 math probability factorial times 7 math probability factorial. And then that's going to give us 30,240 possible ways. So 3 black cars, 7 other cars. Showing all that stuff, there can be your explanation for that. C part, how many different ways could these cars be placed in a row if all the red cars are together, all the black cars are together, and then all the silver cars are together? This does not mean the red cars have to come first, the black cars come second, the silver cars come third. So it just means that the red cars are grouped together, the black cars are grouped together, and the silver cars are grouped together. So again, we have 10 spaces for the cars themselves to go out of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're grouping them with black cars, red cars, silver cars. So these are black cars, these are our red cars, and these are our silver cars. Okay? So black cars, there's 3, 2, and 1. Red cars, there's 2 and 1. Silver cars, there are 5, 4, 3, 2, and 1. Now, this kind of looks like it implies that black comes first, then red, then silver. But so we need to take into account, well, what happens if we're rearranging the colors and red came first, then silver, and then black, or something like that. So we need to do a color choice. Okay, so color choice, you got 3 colors to choose from, and that's 3 colors, 2 colors, 1 color, like that. Okay, so we're going to work those out. It's going to be 6, and then we're going to multiply all this together. That's 6, 2, 20, and 6 would be 120. I'm just multiplying instead of using the factorials. I can do that math in my head pretty easily. So we're going to multiply all these together. 6 times 6 times 2 times 120. And that I do need the calculator. 6 times 6 times 2 times 120. 8,640 ways. All right. Now, let's look at the next set of problems. Card is dealt from a standard 52 card deck, so we've talked about that before. So we know that there's 4 suits, 13 cards in each suit, 8s through king. The suit and the value of the card is recorded. The card is recorded in the deck, and then put back and shuffled, and total of 4 draws are made. One selection consists of those 4 card draws from theirs. Okay, so how many different selections can occur? So, well, we're making a 4 cards in a selection, so we got 4 blanks to choose from. And the way that they've described the selection process is you pick a card, so there's 52 to choose from, and then once you've gotten that card, you write down what it was, and then you put it back. So the next time you pick a card, there's 52 cards again. And then the third time, there's 52 cards again. And then there's 52 cards for the 4th choice. And we're going to multiply all those together. That's the same thing as saying 52 to the 4th power. And we're going to work that out. So depending on what grade level you are and what concept you're dealing with there, you might want to use exponents, you might not. So I'm going to use 52 raised to the 4th power and 7,311,616. That's how many selections there could be out of that. Okay. B part says how many different selections include only red cards. Well, we look at the deck and we say, okay, well, only red cards. Well, that how many choices of red cards are there? Well, there's 26 red cards, hearts and diamonds. Same thing for the second choice. Same thing for the third choice. And same thing for the fourth choice. So we end up with 26 to the fourth power. 26 raised to the fourth. 456,976. All right. How many different selections will include only diamonds? Okay, so we're narrowing it down even further. How many diamonds are in a deck? There are 13 diamonds in a deck, so there's 13 choices to pick a diamond on the first card selection. Put it back. 13 on the next one. Put it back. 13 on the third one. 13 on the fourth one. 13 to the fourth power. 28,561. Important to notice that this is not half of B part, and B part is not half of A part. That we're looking at each individual card selection separately, and we're multiplying all this together. It does not, it's not a straight. It's exponential growth in things here with the selection and the counting process here. Not necessarily just linear with the division. Okay, D part, same scenario. How many different selections include only odd numbered cards? So odd numbered cards would be the 3, the 5, the 7, and the 9. Ace is not an odd numbered card. It's considered a face card. Jack, King, and Queen are face cards. So we only have four for each suit. So there are 16 odd cards. So again, 4 blanks, 16 for the first choice, 16 for the second, 16, 16, 16 to the fourth power. 65,536. E part, how many different selections would include 4 cards of the same value? Okay, so same value, 4 cards of the same value. So that could be, if you pick a 3 of hearts, it's got the same value as a 3 of clubs or 3 of spades or 3 of diamonds out of that. So we could all right, so the first draw decides what card we have. Okay, so 52. You're just picking a card. And then the next card has to match that value. Well, how many cards match that value? 4 of them do. Because if you draw 3 of hearts on the first card, you put that 3 of hearts back, you shuffle, and you pick again. There's a 3 of hearts, a 3 of diamonds, a 3 of spades, and a 3 of clubs. There's 4 cards that have that same value. So we've got to have 4 for the second choice, 4 for the third choice, 4 for the fourth choice. So we really have 52 times 4 to the third, or just type that out all at once. 52 times 4 times 4 times 4, 3,328. Okay. I have a similar idea for F. How many different selections will include identical cards? So identical means 3 of spades, 3 of spades, 3 of spades, 3 of spades, 4 of the same card. So 4 of a kind out of that. So we got 4 blanks again. And again, like part E, the first card we draw decides what we're looking for next. So the first card, there's 52 choices out of that. And then the second card has to match that exactly the same. Not the same value, but the same card. So how many cards match a 3 of diamonds? 1. And That goes for all three of the next choices. So there's only 52 selections that are 4 of a kind. And this is where you get into why is it that a certain card hand beats another in poker or Texas Hold'em or some things like that. It's because there are fewer of those card hands that exist. And then G here, how many different selections will include cards that alternate in color? Okay, so again, alternating in color, we got 4 choices. The first card decides. It's either a red card or a black card. And then the second choice has got to be the other one. So whether we pick red or black in the first choice, the second one's just going to be half of the possible. And then the third one's got to be half again, half of that original set, and then half third one. So we have 52 times 26 to the third. 52 times 26 third. 913,952. Counting principle just gets us introduced to it and gets us thinking about those. And again, drawing those blanks and then thinking about what can go in there are the way you want to start doing that. And we'll get a little bit better. We'll do another activity with counting principles next week. But you guys are doing fine. Hang in there. We're going to make it through this semester. But email me if you got questions.